Hello, community. Can you imagine? Plus 159% performance increase with a new method called TTRL. Is this unbelievable or not? Let's take Gemini 2.5 Pro and let's have it, and I do a summarization of the main achievement of the new AI research paper, and I provide the PDF, and here we have it. We have here, it boosts here the performance by approximately 159%. And this is unbelievable, I can tell you, because look at here the original paper. And here we have it, AIM 2024. And you look at this, yes, it is 159%, but you might say, hey, wait a second here. Because this sounds real familiar, 43.3 on an AIM 2024. I just noticed from my very last video, you remember? Here in the video where I showed you about a TTRL called Luffy, we had a look here at an optimized GRPO with a different normalization. We had OAT, and guess what? OAT achieved on AIM 2024 43.3. You remember this was here the paper? And we discussed this here in relation to other methods of reinforcement learning. And we had here a more advanced, if you want, GRPO implementation. So if this already brought us 43.3%, what do you mean we have again 43.3%? So this means we just achieve state of the art. And you remember in my video about Luffy, I showed you that Luffy achieved 29.5% because it had a little correction to OAT 07B. You know, from the original 43, suddenly it was just 31 and 29. And you say, this is strange. Okay, so what does it mean? So let's have a look. So we have already here with OAT 07B 43.3. And then if you look at AMC, we have 66 with Luffy. And they claim AMC 67. And with MAT 500, they claim 84. But with MAT 500, we already have 88 as SOTA. No? So what's happening here? Are you measuring this and not against state of the art? Are you measuring this against the simplest benchmark here, the Q1 2.5 MAT 7B, without any further improvement of the last, I don't know, half a year? So this was a little bit of a drawback now, realizing this. But you know what? Realizing that suddenly we have 43.3 and 43.3 here from different methodologies. This is a test time optimization, and this is a GRPO train time optimization. I said, hey, now I have a brand new question. Did we hit almost the identical upper limit with different methodologies? Or otherwise, did we hit the same performance wall just from different dimensions? Now, this gets interesting, but from a complete other point of view. So, whatever your AI might tell you is not of relevance anymore, because my channel provides here more value to my audience, and I show you the performance data that AI tells you are not the real state of the art. The different perspective of a new research is what's really interesting in this paper. And even more value for you, I will show you here the benchmark of an off-policy zero reinforcement learning, and we will compare it here to the test time compute scaling with TTRL. So you know when to use a trained model or to go with inference scaling. Wow, this changed rapidly the perspective of this video, but this is what makes it interesting, huh? Because you remember in my last video, I was talking here about pre-training, continuous pre-training, supervised fine-tuning, and then all the reinforcement learning from GRPO, from R1, from R1 MAT, from R1 0, DPO, TPO, and whatever we had. And now we are standing more or less at the same question. And you remember I told you this here in my video, and this is the video No AI Self-Improvement with Reinforcement Learning. And the question was, hey, is it possible to have reinforcement learning that this induces now new reasoning capability beyond the pre-trained base model? You know, the emergence of artificial intelligence, and suddenly out of the darkness arises here new added intelligence. And you know, I have watched my video, it is just wishful thinking. But this did not happen in the training time compute optimization. So guess what? Now we have the same wish. Hey, what about test time scaling? Maybe it is happening here. Hope never dies in AI. So let's have a look, and now you understand maybe here why we'll have a look at test time RL now. TTRL, test time compute scaling of reinforcement learning with a self-labeled reward structure with on-policy labels. This would be the official title, to be absolutely clear what we are talking about. And the spark of genius that will amaze you is the authors tell us, you know, our TTRL has here a pre-trained LLM, and now we let the LLM self-evolve on incoming test inputs. And this is now interesting because we're here on policy, and you know exactly what it means if you have watched my last video. So this means every prompt a model samples n solutions, derives a pseudo-label by a majority voting of the model, converts that label into a binary reward signal, and applies here simple a binary reward on policy reinforcement learning update via GRPO, or you can go with the classical PPO. Now my viewers know that I have here my own wording. So in my wording, this means the language model generates multiple reasoning traces here for one query. The model judges itself on the quality of these reasoning traces by a majority vote, or if you have agent, let the agent do the majority vote for you. Then the model rewards the winner of its own majority vote, the reward signal +1. Then the model self-feeds this +1 reward signal with the winner reasoning trace to its own on-policy reinforcement learning. This is something where you might ask yourself, are you sure that this will evolve here into something? Now let's have a look here at the official professional wording. So it's the same, but now with a little bit more scientific background. Yeah? So it says here, TTRL views its own multiple guesses as a miniature crowdsourced annotation pool. If most hypotheses agree, the answer is probably right. Matching it should be rewarded. Conversely, contradicting the consensus should be penalized. So by iteratively applying the self-referential reward function, the model gradually shifts the probability mass towards answers that tend to become the consensus, thereby improving a single sample accuracy. Importantly, because the vote is recomputed after each policy update, the supervisory signal also improves, forming a positive feedback loop. Now, I hope you are impressed with this wording, because now comes my personal example for you, because I want to provide more value than just an AI summarization for you as my audience. Now I want to give you an example that you might remember as a self-referential example. Let's say one day I ask myself a question, and I'm now this AI system, yeah? And I say, hey, am I beautiful? And you know, it's more or less a 50-50 chance. And it depends if it's sunshine, it depends if it's a mirror close by, so it would have here a ground truth. But let's say on this particular date, it's just a fluctuation in time. I decided I am beautiful. Now, I train my internal reinforcement learning on this. This means my brain says, yes, you are beautiful. Now, the very next morning, with this trained, I come back down here in the morning to my breakfast table and I think, hey, I'm beautiful. Isn't that great? And I apply this reinforcement learning now. My brain does it automatically. And the very next day I come back to my breakfast table in the morning, I say, hey, I'm really, really beautiful. Now we have this self-generating loop with a self-referential reward without any external ground truth fed into the feedback loop. So guess what? On the 10th day, I come down to my breakfast table and I say, I am God. I am beautiful beyond compare. Now you might see that there might be a tiny little insignificant detail in this self-referential feedback loop, because what happens to the AI model is maybe not what we expect. Again, let's have here a look what's happened. We have moved now augmentation from our, if you want, training time compute now to the test time compute scaling. And you remember, in the training time compute, we said the number of samples are so important. If we have here a sample time of 16 samples, you remember here the base was in green and reinforcement learning here was in orange. Now let's say we have 16 samples here and we have here the base model at, let's say, 40% and the reinforced model here at 50%. And you remember what we did? We said, okay, so we kind of learn now this 16 times here as a guidance for the learning process of our LLM. And now what we do today is we just shift it over to the test time scaling. So we say, okay, we now think in the normal training time computation, our reinforcement learning did just one step, but now in the test time, we do the 16 step. So guess what? Is this the identical wall? It is not absolutely identical, and as a homework for you, please explain to me in the comment why there's still a difference. Only if you really would like to do this. So there's another instruction here in this new AI research paper that says setting the temperature now, of course, of our model to max, to 1, as opposed to 0.6, for example, increases now the output entropy. And this now kind of promotes an extensive exploration phase that allows now the model to make better use of its prior knowledge for self-improvement. Now, in my last 2 videos, you know this. And especially in my last video, I showed you we have the training data from another publication. And here on the video Luffy, this is here the thumbnail for the video, we have this one. And in orange, you see the on-policy reinforcement learning. And let's say we do an interpolation, and if we increase the temperature here on the x-axis, you see, yes, this has an inclination to go upwards, yeah? And then in whatever, green or whatever, we have supervised fine-tuning. And supervised fine-tuning we have here quite stable if you ignore this outlier here. But then with higher temperature, it's going down a little bit, yeah? And you remember with Luffy, it was the same thing. We said up till 0.6, it seems that the new Luffy on policy and off policy combined for 0RL is almost equal to the supervised fine-tuning. Look, if we ignore this, this is almost equal. No? And at 0.6, and what a coincidence, we find the 0.6 here also in this publication, then if we say, let's be creative to our mathematical model, Luffy increases, and supervised fine-tuning as a mathematical model that is now creative, whatever this means, has a decreasing performance. So we know this effect. This is nothing new. Now to argue that this higher creativity, this higher uncertainty is an exploration, it's a really interesting interpretation, and it makes better use of its prior knowledge. This is the correct statement. Because remember, the prior knowledge is the pre-trained base model. And we know that the reasoning is based on the pre-trained base model. So, interesting to see the 0.6 that we saw here in my last video, now also here in this video. Now let's have a look at the detailed facts as published. And here we have now the study TTRL, Test Time Reinforcement Learning, Tsinghua University and Shanghai AI Lab. Beautiful. They also have a GitHub. Please go there. You find the information over there. But I look now at the theory. I want to explain the core idea. I want to understand what are they doing? Why are they doing this? And it is published for me yesterday, April 22, 2025. So here we are now, reinforcement learning with a self-labeled reward, which might have some drawbacks, as I have hopefully demonstrated in my example, during the test time compute scaling. So now we moved over to test time or inference scaling. And now we have this statement. TTRL provides evidence that even smaller LLMs can now effectively self-improve on, and now, input-only challenging tasks through reinforcement learning, enabling, and now hold on to your seats, enabling continual learning. Now here again, the hope. We find an AI that will become infinite intelligence just by continual learning on self-improving on input. And we do this by reinforcement learning. So we can reach infinite wisdom just by applying a known methodology, and the AI will do this in a self-improved manner. I mean, it's Christmas and Easter and I don't know what celebration, all happening at the same time. And you know, whenever something seems too good to be true, guess what? It is not true. So I disagree with this statement by the authors here of Tsinghua University. I know they are one of the best universities in the world. I know this. But I would like to prove to you that why I disagree with them. And you know, with RL, it's always this fragile balance between exploration and exploitation. Remember the flashlight? You shine a light in a dark room in front of you and you explore with your flashlight the room. And if you have an exploitation phase, you found an object in this dark room, and now you focus on this reasoning trace, on this object in the dark room, and you want to exploit it more, deeper levels to come to an answer. This is again what's happening here. And now I ask you to be a little bit more scientific and precise, no? Is a pause at 8 already a continual learning? And you might say, hey, that's a strange statement. What do you want to tell me? Well, remember this? Remember this, AIM 24? We said if the number of samples I pass at 8 here we have it. And we have here the base model. And this is here, let's say, at 30%. No? And then we have here the reinforcement learning on policy. Let's say this is, never mind, 50%. So there is a performance improvement, of course. Because we have had a training process going on where we had a modification of the tensor weight and all our transformer layers and so on. So, continual learning, I doubt it. Why? You know that the pre-training of the LLM is the most important criterion for improved reasoning traces with higher K. And you see it here. This here is a very small Qwen 2.5 Mat 7B model. And given time, the number of samples K going up 256, 512, you see the performance of the base model in green goes up 60%, 70%, 80%. And let's say we take 2,000 steps or 5,000 steps, maybe the base model already comes close to 90% of this very simple mathematical benchmark AIM24. So given enough time, given enough tries, the LLM here shines a flashlight in the dark place to explore here the solution space. And if it shines 256 flashlight impulses into the dark room, it will find a solution. Because in this room, think about it's a boiling water, no? And instead of a water molecule in the water, we have reasoning traces. There are so many reasoning traces. 99% might be complete nonsense reasoning traces, but from the rest 1% of the reasoning traces, there's 0.0001% is also there. So just give them enough time. If it is in the pre-training data of the base model, we can reach 80-90% for a simple task. So, and now what's happening? Now what is happening is a posit 8 continued learning. So what we do here, let's say we run 8 different answers. We have a majority vote by TTRL, and we get the best reasoning back. And this is now with a reward signal of +1 fed into our classical reinforcement learning process during test time. So what we have is that at particular, let's say 8 here, we have now a performance level of, let's say, 50% of the reinforcement learning achieved after reinforcement learning. But now look, the base model would also have achieved the same level of accuracy, just taking a little bit longer, let's say 16 or whatever it is. So you see, you would not need reinforcement learning at all, because as this shows us here, the base model would arrive there, just given more sample size. This is now interesting. And now the argumentation is, yes, but I don't need more sample size because I can train now the model here. I bring it back, the system self-improves, and now we are here. And now that the model has modified the internal tensor weights here and all the transformer layers, the next 8 steps starts here, no? And we go here then 8 steps here, so maybe we are here at 60%. And then we train here the result that would be achieved here at 64% with the base model. And we bring here the reinforced learning model higher and higher. Yeah, but the base model would also achieve this without any reinforcement learning, without any on-policy reinforcement learning. And you see the base model would even exceed the performance of on-policy reinforced learning, as shown here in this graph. So the question is now, hey, is this a better, faster, cheaper solution than just let the base model run and explore the complete dark space, explore the complete solution space of this pre-trained base model? Because the solutions are there. You just have to run a lot of sample size to find it. If you want to have a more complete and detailed solution to this, this is the thumbnail to my video. You find it here in this video at 22 minutes and 40 seconds. And I explain much more. And I even tell you what is this beautiful dark line that is so much more powerful. Okay, so let's come to a close here. The authors of TTRL tell us, hey, we observed that as the question difficulty increases, both the performance improvement and something else decreases. Now this supports my theory. No? The moment the question becomes more difficult, TTRL performance improvements decrease, fail. Of course, because the knowledge to generate valid reasoning traces is not in the pre-trained model. Therefore, you can't test time RL it out of the model if it's not in the base model. And I understand the hope that reinforcement learning will provide the emergence of intelligence. But hey, as scientists, we have to be real, no? It is possible in little tiny steps that you can go further and you bring the result back from a 16K to an 8K model. But there are limits, and they say there are limits. And if you find here, and this is here the thumbnail of my video where I showed you, UC Berkeley investigated this, how to make smaller LLMs R1 smart. Here at 11 minutes and 12 seconds, we looked at the exact same topic. And here I explained to you, hey, what is happening if we have medium questions, hard to solve question, and extreme hard to solve question. So the complexity level of the reasoning traces would increase. And you see, for some particular AIM-25, so more advanced questions, the model here for the hard, it fails. It goes down. The harder the questions become to solve mathematically, the model fails and fails and fails. And I tell you what countermeasures we can do. For example, here we have to fine-tune on 1K long R1 style trajectories, but here R1 style are off policies, SFTs, so something completely different. But you see, it is the same wall, just from a different dimension. And there's also, and this is what I like in this study, they're absolutely transparent. And they say TTRL is not fundamentally different from all the other existing reinforcement learning algorithms, and therefore inherits several of the characteristics of RL, such as the sensitivity to the data difficulty, complexity, hard to solve question, the strong reliance on the priors. And you know, the priors are the capability of the pre-trained language models. The reasoning traces over there. So the reliance on the pre-training and the risk of collapse. And this is all true. So they see their inherent limitation. And in my last video on Luffy, I showed you the entropy collapse that can happen and measures how to circumvent here the entropy collapse with some additional mathematical terms in or for the optimization problem, the mathematical optimization problem. You find this in Luffy. So yes, it is not different, and we have the same problems in reinforcement learning. And I have to tell you, if you do the reinforcement learning in the training time before inference, or if we do the reinforcement learning in the inference time, in the test time compute scaling, it is not there. Yes, there is a little difference, but in general, it is the same reinforcement learning. So what a surprise. They say, yeah, strong reliance on priors from the pre-training. So I understand that they want to position this, yes, we have here a continuous self-learning of the system, but I would say only in a very limited time, in a very limited area of complexity, because look at just if you increase the number of steps, K, from 8 to 16, this is the only improvement you can achieve. And if you want to call this continuous self-learning, I'm with you. But be advised, only in a very, very narrow domain of reasoning traces to solve complex problems. Outside of this domain, you fail completely. And there is no infinite continuous self-learning. And you know, there's another small, I would say almost irrelevant problem that I see that was not mentioned here in the paper, and this is error propagation. Continuous linear error propagation of TTRL is happening now in test time. This means in real time. This means there's no going back and trying another branch, let's say in a Monte Carlo tree search that we do. But this means it is forward. And this is heaven for error propagation. So maybe learning from quantum computing, maybe we need advanced error correction code if you want to apply TTRL. But you know what? I see another problem for the real-world application of TTRL that is not mentioned in the paper. So these are just my thoughts, yeah? Because this means we have a complete RL in test time compute. So we modify now the tensor weights of our transformer architecture, even if we freeze some of the layers, never mind, during inference compute. I mean, are you real? You know what it means? This means quite massive, quite expansive, especially for bigger LLMs. And if I say I want to do this and I want to start a query with TTRL on, let's go crazy, on an R1 model with 671 billion pre-trainable parameter, I have to have the compute infrastructure, let's say hundreds of NVIDIA H100 GPUs or Blackwell GPUs, to run here the complete update of the tensor weights of this mixture of expert system in all layers, and I do this in real time, and then I wait for the answer to be generated. Wow, this has immense implication on the compute infrastructure if we want to do this update of the complete tensor weight structure just for a query in real time. This does not mean only that we have to wait, I don't know, given the complexity of the query, 10 minutes, 20 minutes, half an hour, 2 hours, 5 hours, 10 hours. But we have to run hundreds of NVIDIA GPUs at full power because we compute here an update of all the tensor weights. So this is now a methodology. Just I give you some personal thoughts about this and, added value to my customer you might not find in the official publication. But I would just want to stress, it's a beautiful publication by Tsinghua University. They really try to bring it over now, what we learned here from the training time compute to the test time compute. But I think we just have to be aware of further limitation that happen. And maybe it's better to train the model, one time at the training time and then have this model execute maybe another optimization process in test time compute scaling and inference scaling. What you see is that all the videos here of the last week and even more have one topic. They all focus here on one topic: how to make AI more intelligent. And I know they hope to make it self-learning, self-improving, continuous learning. I understand this hope. I understand this wish. I understand the desire that you say, I just start the engine once and then the AI does it all by itself and I don't have to care anymore. I understand the desire, but let's be real. We have to understand the mechanisms, we have to understand the theory, we have to understand the limitations, we have to question and compare all the different experiments. And like today, at the very beginning of this video, you see sometimes you discover the same limits. And if you come now from the training time or if you come from the test time dimensions, it doesn't matter. You find the same wall in front of you. And this is valuable information. This is amazing to understand because you know what? Now we can try to break through these walls for multiple dimension in parallel. We just have to be a little bit more clever. We just have to learn more. So really interesting what the next week will bring. If you are interested, hey, why not subscribe? And I see you in my next video.